Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 16th century in Italy witnessed a fervid pursuit of solutions to cubic equations, a mathematical challenge that captivated scholars and sparked intense rivalries. Amidst this intellectual ferment, a curious phenomenon emerged: the appearance of expressions involving the square root of -1 within the solutions generated by Cardano's formula. These impossible numbers, as they were often regarded, presented a profound dilemma. Mathematicians of the time grappled with their perplexing nature, unsure whether to dismiss them as mere computational artifacts or to explore their potential mathematical significance. Rafael Bombelli stands as a pivotal figure in this historical narrative. Unlike many of his contemporaries who shied away from the square root of -1, Bombelli dared to confront these enigmatic entities head-on. He embarked on a systematic investigation, meticulously exploring their properties and developing rules for their manipulation. His groundbreaking work, culminating in his treatise Algebra, laid the foundation for the development of complex number theory, transforming these previously dismissed impossible numbers into legitimate and powerful mathematical objects. This exploration delves into Bombelli's algebra, examining its structure, content, and, most importantly, its innovative treatment of complex numbers. We will investigate his unique notation, his rules for performing arithmetic operations with these numbers, and his overall contribution to expanding the boundaries of mathematical thought. Furthermore, we will trace the influence of Bombelli's work on subsequent generations of mathematicians, highlighting its enduring legacy in shaping our understanding of the number system. Born in Bologna, Italy, in 1536, Rafael Bombelli initially pursued a career far removed from the abstract realm of mathematics. He trained as an hydraulic engineer, a profession that demanded practical skills in surveying, construction, and water management. His expertise in this field led him to work on various projects, including the reclamation of marshlands of the Pontine Marshes, a challenging undertaking commissioned by the papal government. Despite his successful engineering career, Bombelli harbored a deep interest in mathematics. This passion eventually led him to undertake a comprehensive study of algebra, focusing specifically on the solution of cubic equations. The prevailing method for solving these equations at the time was Cardano's formula, a complex expression that often yielded solutions involving the square root of -1, even when the final result was a real number. This apparent paradox deeply intrigued Bombelli. He recognized that Cardano's formula, while providing a means to obtain correct solutions, also introduced these seemingly nonsensical quantities into the intermediate steps. Instead of dismissing them as meaningless, Bombelli saw an opportunity to explore their behavior and determine whether they could be manipulated in a consistent and logical manner. This quest to understand the square root of -1 became the driving force behind his magnum opus, Algebra. Bombelli's Algebra is structured as a comprehensive treatise on algebraic principles, encompassing arithmetic operations, equation solving, and various other topics. However, its most significant contribution lies in its systematic treatment of what Bombelli termed più di meno and meno di meno, his notation for the square root of -1 and its negative counterpart, respectively. He meticulously developed rules for adding, subtracting, multiplying, and dividing these quantities, demonstrating that they could be manipulated according to consistent algebraic laws. His motivation stemmed directly from the problem inherent in Cardano's formula. Cardano's method, while effective, sometimes produced expressions containing the square root of negative numbers even when the final result was a real, tangible value. Consider, for example, the cubic equation x cubed equals 15x plus 4. Applying Cardano's formula to this equation yields a solution involving the cube root of 2 plus the square root of -121 plus the cube root of 2 minus the square root of -121. The presence of the square root of -121, or 11 times the square root of -1, is initially perplexing, since the original equation possesses a real solution, namely that x equals 4. Bombelli recognized that if he could develop a consistent set of rules for manipulating these impossible numbers, he might be able to simplify the expression obtained from Cardano's formula and arrive at the real solution. This realization spurred him to define the fundamental operations involving the square root of -1. Bombelli's notation, while somewhat cumbersome by modern standards, represented a significant step forward in the development of complex number theory. He denoted the square root of -1 as più di meno, literally plus of minus, and its negative counterpart as meno di meno, or minus of minus. This terminology, though unconventional, allowed him to clearly distinguish between positive and negative imaginary units. He then proceeded to formulate rules for performing arithmetic operations with these quantities. For instance, he stated that più di meno times più di meno makes meno, meaning that the square root of -1 multiplied by itself equals -1. Similarly, meno di meno times meno di meno makes meno, indicating that the negative square root of -1 multiplied by itself also equals -1. These rules, though seemingly simple, were crucial for establishing a consistent algebraic framework for manipulating complex numbers. Furthermore, Bombelli provided rules for multiplying real numbers by più di meno and meno di meno. He stated that 2 times più di meno makes più di meno, meaning that a positive real number multiplied by the square root of -1 yields a positive imaginary number. Likewise, più times meno di meno makes meno di meno, indicating that a positive real number multiplied by the negative square root of -1 yields a negative imaginary number. Similar rules were provided for multiplying negative real numbers by più di meno and meno di meno. These seemingly elementary rules laid the groundwork for a more comprehensive understanding of complex number arithmetic. Bombelli demonstrated that these impossible numbers could be manipulated in a consistent and logical manner, paving the way for their acceptance as legitimate mathematical entities. His work marked a departure from the prevailing skepticism towards the square root of -1, ushering in a new era of exploration and discovery in the realm of algebra. His careful notation, although superseded by more compact modern forms, was instrumental in clarifying the operations he defined, thereby enabling others to follow his reasoning and build upon his insights. The true significance of Rafael Bombelli's contribution lies within the pages of his magnum opus, Algebra. This comprehensive treatise, far from a mere collection of algebraic techniques, represents a systematic exploration of number, equation, and solution, venturing boldly into uncharted mathematical territory. Within its structure, Bombelli unveils a carefully constructed system for manipulating what were then considered impossible numbers, granting them a legitimacy previously unheard of. Bombelli's algebra is structured to progressively build upon fundamental concepts, guiding the reader from basic arithmetic operations to the solution of complex equations. Bombelli's meticulous treatment of complex numbers is a defining feature of algebra. He presents them not as mere curiosities or computational inconveniences, but as integral components of a broader algebraic system. His commitment to understanding and manipulating these numbers is evident in his introduction of a specific notation for the square root of -1 and its negative counterpart. He designated the positive square root of -1 as pu de meno, literally plus of minus, and the negative square root of -1 as meno de meno, or minus of minus. This explicit notation, while appearing cumbersome by modern standards, was crucial for clearly distinguishing between positive and negative imaginary units and for establishing consistent rules for their manipulation. It is important to realize that he did not have the luxury of using I. Bombelli's notation provided a visual anchor for what many considered a slippery concept. The phrase pu de meno served as a constant reminder that he was dealing with a quantity whose square was -1, a concept that defied conventional arithmetic. Likewise, meno de meno clearly indicated the additive inverse of this quantity. This notational clarity was essential for developing and communicating the rules for operating with complex numbers. The heart of Bombelli's contribution lies in his systematic development of rules for performing arithmetic operations on complex numbers. He meticulously outlined how to add, subtract, multiply, and divide these quantities, ensuring that the operations were consistent with the established rules of algebra. These rules, though expressed in the language of his time, are directly equivalent to the modern rules for complex number arithmetic. Consider Bombelli's rule for the addition of complex numbers. He effectively stated that to add two complex numbers, one must add their real parts and their imaginary parts separately. In modern notation, this can be expressed as a plus by plus c plus d equals a plus c plus b plus di. Bombelli articulated this principle using his pu de meno and meno de meno notation, providing concrete examples to illustrate the process. For instance, adding to pu de meno 3 to 5 pu de meno 1 would yield 7 pu de meno 4, accurately capturing the essence of complex number addition. Subtraction followed a similar pattern. To subtract one complex number from another, one subtracts the real parts and the imaginary parts separately. Thus, a plus by c plus d equals a c plus b di. Bombelli demonstrated this with examples like subtracting 1 pu de meno 1 from 8 pu de meno 5 to obtain 7 pu de meno 4. The consistent application of these rules reinforced the idea that complex numbers, despite their seemingly paradoxical nature, could be treated as legitimate mathematical objects subject to the same operational principles as real numbers. Multiplication of complex numbers required a more nuanced approach, demanding careful attention to the interaction between real and imaginary components. Bombelli's rules for multiplication are equivalent to the modern formula of plus by c plus d equals ac bd plus ed plus bc di. He meticulously detailed how to multiply pu de meno and meno de meno with both positive and negative real numbers, as well as with each other. He stated that pu de meno times pu de meno makes meno, which translates to square 1 asterisk square 1 equals 1. Similarly, meno de meno times meno de meno makes meno, reflecting square 1 asterisk square 1 equals 1. Furthermore, pu de meno times meno de meno makes pu, which corresponds to square 1 asterisk square 1 equals 1. These rules, combined with a distributive property, allowed him to systematically multiply any two complex numbers. Bombelli provided numerous examples to illustrate the application of these multiplication rules. For instance, multiplying 2 pu de meno 3 by 4 meno de meno 2 would involve multiplying each term in the first complex number by each term in the second, carefully applying his rules for pu de meno and meno de meno. The result, after simplification, would be a new complex number expressed in the standard form of a real part plus or minus an imaginary part. While the calculations might appear tedious by modern standards, the underlying principle was groundbreaking. Complex number multiplication could be performed systematically and consistently, yielding predictable results. Division, the inverse operation of multiplication, presented a further challenge. Bombelli addressed this by employing a technique analogous to rationalizing the denominator in modern complex number arithmetic. To divide one complex number by another, he multiplied both the numerator and the denominator by the conjugate of the denominator. This process eliminates the imaginary part from the denominator, allowing for the division to be performed as a series of multiplications and additions. Although Bombelli did not explicitly use the term conjugate, his method effectively achieved the same result. He recognized that multiplying a complex number by its opposite, changing the sign of the imaginary part, would eliminate the imaginary component from the product. This allowed him to transform the division problem into a more manageable form involving only real numbers and the fundamental imaginary unit, pu de meno or meno de meno. Consider the division of a plus by c plus d. Bombelli's approach would involve multiplying both the numerator and denominator by c d, resulting in a plus by c d slash c plus d c d. The denominator simplifies to c2 plus d2, a real number, while the numerator expands to ac plus bd plus bc add I. The result is a complex number with a real part of ac plus bd slash c2 plus d2 and an imaginary part of bc add slash c2 plus d2. Bombelli meticulously demonstrated this process with numerous examples, showcasing his mastery of complex number arithmetic. The novelty of Bombelli's approach lies in his unwavering commitment to treating these impossible numbers as legitimate mathematical entities. He did not dismiss them as mere computational artifacts or meaningless symbols. Rather, he embraced them as integral components of a broader algebraic system, developing a consistent set of rules for their manipulation. His work demonstrated that complex numbers, despite their departure from conventional arithmetic, could be subjected to rigorous mathematical analysis. Bombelli's algebra served as a crucial stepping stone in the acceptance and understanding of complex numbers. By providing a clear notation and a systematic set of rules for their manipulation, he paved the way for future mathematicians to explore their properties and applications. His work marked a departure from the prevailing skepticism towards the square root of -1, ushering in a new era of exploration and discovery in the realm of algebra. The systematic treatment of complex numbers within algebra provided a foundation upon which later mathematicians could build, ultimately leading to the development of complex analysis and its profound implications for mathematics, physics, and engineering. His notation, while eventually superseded by more compact modern forms, was instrumental in clarifying the operations he defined, thereby enabling others to follow his reasoning and build upon his insights. Cardano's Ars Magna, a landmark treatise on algebra, presented a general solution for cubic equations. This formula, while groundbreaking, encountered a peculiar difficulty when applied to certain cubic equations possessing real roots. These equations, when substituted to Cardano's method, yielded expressions involving the square roots of negative numbers, an apparent paradox known as the causus irreducibilis. It was in this perplexing situation that Bombelli made a pivotal contribution, demonstrating the power and consistency of his complex number arithmetic. Consider the cubic equation x cubed equals 15x plus 4. This equation, readily solvable by inspection, has a real root of 4. Applying Cardano's formula, however, leads to an expression involving the square root of negative 121. Specifically, the formula yields x equals the cube root of 2 plus the square root of negative 121 plus the cube root of 2 minus the square root of negative 121. This expression, at first glance, seems nonsensical as it involves taking the square root of a negative number. Bombelli, undeterred by this apparent absurdity, recognized the potential for manipulating these expressions using his newly defined rules for complex numbers. He posited that the cube root of 2 plus the square root of negative 121 could be expressed in the form of plus b times the square root of negative 1, where a and b are real numbers. Similarly, he proposed that the cube root of 2 minus the square root of negative 121 could be expressed as a minus b times the square root of negative 1. To determine the values of a and b, Bombelli cubed both sides of these equations, cubing a plus b times the square root of negative 1. He obtained a cubed plus 3 times a square times b times the square root of negative 1 minus 3 times a times b squared minus b cubed times the square root of negative 1, equating the real and imaginary parts of this expression with the real and imaginary parts of 2 plus the square root of negative 121. He arrived at two equations: a cubed minus 3 times a times b squared equals 2, and 3 times a square times b minus b cubed equals 11. Bombelli astutely observed that a equals 2 and b equals 1 satisfied these equations. Therefore, the cube root of 2 plus the square root of negative 121 is equal to 2 plus the square root of negative 1. Similarly, the cube root of 2 minus the square root of negative 121 is equal to 2 minus the square root of negative 1. Substituting these values back into Cardano's formula, Bombelli obtained x equals 2 plus the square root of negative 1 plus 2 minus the square root of negative 1. The imaginary terms cancel, leaving x equals 4, the real root of the original cubic equation. This seemingly simple calculation held profound implications. It demonstrated that complex numbers, despite their apparent lack of physical reality, could be used to manipulate algebraic expressions and arrive at real solutions. Bombelli's method provided a concrete example of how these impossible numbers could be tamed and put to practical use. Bombelli's notation, while distinct from modern conventions, played a crucial role in facilitating these calculations. He represented the square root of negative 1 with the phrase più di meno, meaning plus of minus, and its negative counterpart as meno di meno, meaning minus of minus. Using these terms, he meticulously laid out the rules for addition, subtraction, multiplication, and division of complex numbers. These rules, expressed in his unique notation, allowed him to systematically manipulate the expressions arising from Cardano's formula and ultimately arrive at the real root of the cubic equation. To illustrate the correspondence between Bombelli's notation and modern notation, consider his representation of the complex number 2 plus the square root of negative 1. In Bombelli's terms, this would be written as 2 più di meno. In modern notation, this is simply 2 plus I, where I represents the imaginary unit, the square root of negative 1. Similarly, the expression 2 minus the square root of negative 1, written as 2 meno di meno by Bombelli, is represented as 2 minus I in modern notation. Bombelli's rules for multiplication can also be translated into modern notation. For example, he stated that più di meno times più di meno makes meno, meaning that the square root of negative 1 multiplied by itself equals negative 1. In modern notation, this is simply I times I equals negative 1, or I squared equals negative 1. Similarly, più di meno times meno di meno makes più, meaning that the square root of negative 1 multiplied by the negative square root of negative 1 equals positive 1. In modern notation, this is I times negative I equals 1. Through his meticulous calculations and clear notation, Bombelli demonstrated the internal consistency and utility of complex numbers. He showed that these seemingly paradoxical entities could be incorporated into the existing framework of algebra, expanding its scope and power. His resolution of the causus irreducibilis in Cardano's formula was a triumph of algebraic manipulation, revealing a hidden harmony within the realm of numbers. He provided a bridge between the abstract world of mathematics and the concrete world of real solutions, solidifying the place of complex numbers in the mathematical landscape. The significance of this lies not only in solving a specific problem, but in opening up new avenues of mathematical exploration, paving the way for a deeper understanding of numbers and their properties. Bombelli's Algebra, a testament to rigorous calculation and innovative thought, entered a mathematical world steeped in tradition yet yearning for expansion. The initial reception of his work was, predictably, mixed. The very idea of impossible numbers, entities born from the square root of negative 1, challenged the deeply ingrained notion that numbers should directly correspond to tangible quantities or geometric lengths. Many mathematicians of the time, schooled in the classical tradition of Euclid and Diogenes, viewed these new numbers with suspicion, if not outright dismissal. The challenge lay in demonstrating the validity of these complex numbers. Bombelli undertook this task with a methodical approach, emphasizing the rules of algebra and the consistency of his calculations. He showcased how Despite their seemingly paradoxical nature, complex numbers could be manipulated according to established algebraic principles, leading to meaningful and verifiable results. His solution to the Karsus irreducibilities in cubic equations served as a powerful demonstration of their utility, providing real solutions to real problems through the intermediary of these imaginary quantities. However, persuasion is a gradual process, particularly in the realm of mathematics, where proof and rigor reign supreme. The acceptance of complex numbers was a slow burn, a gradual shift in perspective that unfolded over decades, even centuries. Several factors contributed to this delayed embrace. The lack of a clear geometric interpretation initially hindered their assimilation into the mainstream of mathematical thought. Numbers, for many, were inextricably linked to geometric representations, lengths, areas, or volumes. Complex numbers, lacking such an immediate visualization, remained abstract and somewhat mysterious. Furthermore, the notation and terminology surrounding complex numbers were still in their nascent stages. Bombelli's notation, while a significant improvement over previous attempts, was yet to be fully standardized or universally adopted. The very term, imaginary, carried a connotation of unreality, further fueling skepticism among those who sought a concrete foundation for their mathematical endeavors. It is instructive to compare Bombelli's approach with those of other mathematicians who grappled with these impossible numbers. Girolamo Cardano, despite his initial discomfort with complex numbers, had cautiously introduced them in his own work, Ars Magna. However, Cardano treated them more as curiosities, interesting but ultimately perplexing entities that appeared in the intermediate steps of calculations but did not fully embrace their potential. Rafael Bombelli, in contrast, went further, systematically exploring their properties and demonstrating their consistent behavior within the algebraic framework. Other mathematicians, such as John Mulleys, attempted to provide geometric interpretations of complex numbers, often with limited success. These early attempts, while well-intentioned, often fell short of capturing the full essence of these numbers, hindering their widespread acceptance. It was only later, with the development of the arc and diagram and other geometric representations, that complex numbers began to gain a firmer foothold in the mathematical landscape. The adoption, adaptation, and improvement of Bombelli's notation and methods unfolded gradually. Later mathematicians built upon his foundation, refining his notation and extending his results. His use of parentheses and clear symbolism for the imaginary unit, though not identical to modern notation, paved the way for the streamlined representations we use today. Mathematicians recognized the power of his algebraic manipulations, adapting his techniques to solve a wider range of problems. Over time, Bombelli's work exerted a profound influence on later developments in algebra and number theory. His systematic treatment of complex numbers laid the groundwork for the development of complex analysis, a vast and powerful branch of mathematics with applications in diverse fields, from physics and engineering to computer science and finance. His emphasis on algebraic rigor and consistency helped to solidify the foundations of modern algebra, paving the way for the abstract and axiomatic approaches that characterize much of contemporary mathematics. The evolution of notation is a crucial aspect of this story. Bombelli's notation, while revolutionary for its time, was gradually refined and standardized by subsequent generations of mathematicians. The introduction of the symbol I to represent the square root of -1, while not directly attributable to Bombelli, became a cornerstone of complex number theory, simplifying calculations and facilitating communication among mathematicians. Euler's formula, connecting complex exponentials with trigonometric functions, provided a powerful tool for analyzing and manipulating complex numbers, further solidifying their place in the mathematical landscape. The formalization of complex numbers also played a crucial role in their acceptance. As mathematicians developed rigorous definitions and axiomatic systems for complex numbers, they moved beyond the realm of mere calculation and into the realm of abstract mathematical structures. This formalization allowed for a deeper understanding of the properties of complex numbers and their relationship to other mathematical objects. Bombelli's approach, grounded in algebraic manipulation rather than geometric intuition, proved remarkably prescient. While geometric interpretations of complex numbers eventually emerged, it was Bombelli's focus on the rules of algebra that ultimately unlocked their potential. He demonstrated that these seemingly impossible numbers could be tamed and harnessed through the power of algebraic reasoning, opening up new vistas of mathematical exploration. His legacy is therefore one of both innovation and rigor. He dared to venture into uncharted mathematical territory, embracing the seemingly paradoxical and demonstrating its inherent consistency. His meticulous calculations and clear notation provided a solid foundation for future generations of mathematicians to build upon, solidifying his place as a pioneer in the development of complex number theory. The delayed acceptance of his ideas serves as a reminder of the challenges inherent in introducing radical new concepts into the established order, highlighting the importance of perseverance, clarity, and unwavering faith in the power of mathematical reasoning. Bombelli's contributions resonate far beyond the specific algebraic techniques he employed. His lasting impact stems from his systematic approach to complex numbers and his unwavering conviction in their utility. He didn't simply stumble upon these numbers. He meticulously dissected them, defined their properties, and demonstrated their power in resolving seemingly intractable problems. This methodical exploration, more than any single equation, cemented his place in mathematical history. The significance of Bombelli's work lies in its demonstration that mathematical innovation can arise from embracing the unconventional. In a time when negative and imaginary numbers were viewed with suspicion, he dared to treat them as legitimate mathematical objects, subject to the same algebraic rules as ordinary numbers. He did this without relying on geometric interpretations, which were still nascent at the time. This willingness to challenge conventional wisdom, to push the boundaries of what was considered acceptable, is a hallmark of true mathematical pioneers. His work paved the way for the gradual acceptance of abstract mathematical concepts. By showing that these seemingly nonsensical numbers could produce meaningful results, he helped to erode the resistance to ideas that lacked immediate physical intuition. This was a crucial step in the development of modern mathematics, which relies heavily on abstract concepts and formal systems. To fully appreciate Bombelli's legacy, it is helpful to consider the evolution of complex number theory since his time. While he focused primarily on algebraic manipulation, later mathematicians developed geometric representations of complex numbers, providing a visual way to understand their properties. The Arkin diagram, for instance, represents complex numbers as points in a plane, with the real part corresponding to the horizontal axis and the imaginary part corresponding to the vertical axis. This geometric interpretation greatly simplified many calculations and provided new insights into the nature of complex numbers. Furthermore, Euler's formula, which states that e to the I theta equals cosine of theta plus I times sine of theta, established a profound connection between complex numbers, trigonometric functions, and exponential functions. This formula has far-reaching implications in many areas of mathematics, physics, and engineering. It allows for the elegant representation of oscillations, waves, and other periodic phenomena. These later developments, however, do diminish Bombelli's initial contribution. His work provided the essential foundation upon which these later discoveries were built. He demonstrated that complex numbers were not merely a curiosity, but a powerful tool that could be used to solve real problems. He established the basic rules of complex arithmetic, providing a framework for future mathematicians to explore their properties and applications. Bombelli's exploration of complex numbers highlights a fundamental aspect of mathematical discovery: the interplay between intuition, rigor, and application. He began with a seemingly paradoxical idea, the square root of a negative number, and, through careful analysis and calculation, he transformed it into a valuable mathematical tool. His work demonstrates that mathematical progress often requires a willingness to embrace the unfamiliar, to challenge established assumptions, and to persevere in the face of skepticism. His influence extends beyond the realm of pure mathematics. Complex numbers have become indispensable tools in many areas of science and engineering. They are used in electrical engineering to analyze alternating current circuits, in quantum mechanics to describe the behavior of particles, and in fluid dynamics to model the flow of liquids and gases. These applications are testament to the enduring power of Bombelli's initial insights. Bombelli's legacy is a reminder that the pursuit of mathematical knowledge is a journey of exploration and discovery. It requires a combination of creativity, rigor, and a willingness to embrace the unknown. His work stands as a testament to the power of human intellect to unravel the mysteries of the universe and to create new tools for understanding and manipulating the world around us. His approach, grounded in the consistent application of algebraic rules, is particularly noteworthy. Unlike some of his contemporaries who sought geometric justifications for algebraic manipulations, Bombelli focused on the internal logic of the mathematics itself. He showed that complex numbers could be manipulated according to the established rules of algebra, yielding consistent and meaningful results, even without a clear geometric picture. This emphasis on formal rules, rather than geometric intuition, foreshadowed the development of modern abstract algebra, which emphasizes the study of algebraic structures independent of their specific interpretations. The beauty of Bombelli's work resides in its elegant simplicity. He did introduce complex numbers as bizarre, impossible entities. Instead, he treated them as ordinary numbers subject to the same algebraic rules. This simple yet profound idea unlocked a wealth of mathematical possibilities, paving the way for future generations of mathematicians to explore the rich and complex world of numbers. His story is a testament to the enduring power of mathematical curiosity and the importance of challenging conventional wisdom. He dared to venture into uncharted territory, embracing the seemingly paradoxical and demonstrating its inherent consistency. His meticulous calculations and clear notation provided a solid foundation for future generations of mathematicians to build upon, solidifying his place as a pioneer in the development of complex number theory. Consider the inherent human tendency to categorize and define, to create boundaries between what is known and what is unknown. Bombelli, in his exploration of complex numbers, blurred these boundaries. He demonstrated that the seemingly impossible could become possible, that the abstract could become concrete, and that the unconventional could lead to profound insights. This willingness to challenge the status quo is a vital ingredient in all forms of scientific and intellectual progress. The acceptance of complex numbers was a gradual process, spanning centuries and involving the contributions of many mathematicians. Bombelli's work was an early and crucial step in this process, laying the groundwork for future generations to build upon. He demonstrated that these numbers were not merely a mathematical curiosity, but a powerful tool that could be used to solve real problems. His legacy serves as an inspiration to all those who seek to push the boundaries of knowledge. It reminds us that the most profound discoveries often come from challenging established assumptions and embracing the unconventional. As we continue to explore the vast and ever-expanding landscape of mathematics, we owe a debt of gratitude to Bombelli, the pioneer who dared to venture into the realm of the imaginary and revealed its hidden treasures. His meticulous approach to algebra illuminated the path for future generations of mathematicians, forever changing our understanding of numbers and their profound implications.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.